I want you to close your eyes for a second. Picture a factory. What do you see?
Probably sparks, robotic arms, a conveyor belt.
Exactly. Loud, heavy, slow. Now, I want you to just erase that image. Replace it with a single small glass jar on a table. It's filled with this clear liquid. Looks just like water.
Okay.
You blink, and I mean that literally, one blink, and inside that jar, a complex, solid statue has just appeared. It's floating there. It wasn't built. It's sort of manifested.
That sounds like a magic trick, or maybe a glitch in a video game rendering engine.
It really does, but it's not magic, and it's not a simulation. This is the reality described in a new paper in Nature that we are tearing into today. We're looking at a technology called DISH.
Which stands for, and it's a bit of a mouthful, Digital Incoherent Synthesis of Holographic Light Fields.
Right. But the acronym, DISH, works. And the headline here is just wild. Sub-second volumetric 3D printing.
We're not talking minutes. We're talking about printing complex millimetre-scale objects in, what, 0.6 seconds?
0.6 seconds. And just to set the stakes early, this isn't just about making things faster. It feels like a fundamental shift in how we create matter.
Oh, absolutely. If this technology scales, we could be looking at the end of assembly as we know it.
So let's back up for a minute.
Yeah.
To understand why 0.6 seconds is so insane, we have to talk about how slow normal 3D printing is.
Right. Most people have probably seen one. The little nozzle buzzing around, building something up layer by layer.
It's agonizing. I printed a phone stand once. It took like 6 hours.
It is slow, but there's a bigger problem, which is anisotropy. Because you're stacking these layers, the object is actually weak in one direction. It's like wood grain.
If you pull it the wrong way, it just snaps along those layer lines.
Exactly. And you get those little staircase ridges on the surface. It's not smooth.
So to fix this, the industry came up with something called volumetric additive manufacturing. I've heard this described as a reverse CT scan. Is that right?
That is the perfect analogy. Think about a hospital CT scan. An X-ray source spins around you, taking 2D pictures from every angle.
And then a computer stitches them all together into a 3D model.
Precisely. Volumetric printing does that completely backwards. You take a vat of photosensitive gel, a liquid that turns solid when it gets hit by enough light.
And you project light patterns into it from all these different angles at the same time.
Exactly. And where those beams of light intersect and cross, the energy dose spikes. It crosses a certain threshold, and the liquid solidifies instantly.
The whole object just materializes at once.
This whole thing, no layers, no ridges, just a solid object appearing out of nowhere.
Okay, so if that already existed, they call it CAL, right? Computed axial lithography.
That's the one.
So why did these researchers need to invent this new DDS method? What was broken with the old way?
The spinning.
The spinning.
In the old method, to get light from all those angles, you had to rotate the sample. You literally put the jar of resin on a motor and spun it around.
Oh, I can see the problem already. If I spin my cup of coffee, it creates a vortex. It sloshes everywhere.
Exactly. Centrifugal force. The surface deforms, the liquid gets agitated, and you have to remember, we're trying to print features smaller than a human hair. You can't paint on a canvas that's sloshing around, you just get a blur.
So how did they deal with the sloshing before?
They cheated. They used super high viscosity resins, basically goo, thing honey, or, even thicker. If the fluid is incredibly thick, we're talking 6,000 to 10,000 centipoise, it doesn't slosh as much when you spin it.
But then you're stuck printing with peanut butter. You can't use these thin, water-like fluids.
And that is a massive limitation. It kills your speed because thick goo flows slowly. And crucially, it kills almost all the biological applications.
Right. You can't put living cells in a thick syrup and spin them around at high speed.
They'd never survive. So this is where DISH has its aha moment. The researchers looked at this spinning jar of goo and just asked, why are we spinning the jar?
It's such a simple question.
It's a classic engineering inversion. If spinning the sample is the problem, then start moving the sample.
Keep the jar still.
And spin the light instead.
So this is the rotating periscope I read about in the paper.
It's this brilliant piece of hardware. They built a mechanical periscope that physically whips around the stationary container. And I mean whips. It's doing up to 10 rotations per second.
That's 600 RPM. That's incredibly fast for a mechanical arm.
It is. But because the vibration is in the machine, not the liquid, the resin in the jar is perfectly calm. No sloshing, no centrifugal force.
Which means they can use the runny stuff.
Exactly. They can use low viscosity materials. The paper mentions a viscosity of around 4.7 centipoise. Water is 1. Honey is thousands. So this is basically like printing in milk.
And that's actually the secret to the speed, isn't it? The low
A
viscosity.
huge part of it, yeah. With thick resins, after you print something, you have to wait for the goo to slowly flow back in and fill the gap. It takes time. With a watery liquid, the reflow is instantaneous.
So we have a stationary jar, spinning light, but speed is only half of it. If you print a blob in zero point 0.6 seconds, who cares? It has to be precise. And this is where the holographic part of DSH comes in.
This is the part that really got me. This is where they had to, like, fight the laws of physics.
Okay, so let's unpack the optics here. Usually with a lens, there's a trade-off, right? If you want super high resolution, like a macro photo of an insect, you get a tiny depth of field.
Exactly. The bug's eye is sharp, but its legs are all blurry. High resolution means shallow focus. The paper says their lens has a native depth of field of only 0.4 millimeters. That's paper thin.
But they're printing objects a centimeter thick. So shouldn't like 95% of the object be a fuzzy, out-of-focus mess?
In the old world of ray optics, where you treat light like straight lines, it absolutely would be. But DSH uses wave optics. They treat light as a wave that diffracts and interferes.
And diffraction is just light spreading out as it passes through a lens, right?
Right. Usually it's the enemy because it causes blur. But these researchers, they embraced it. They used a coherent laser, a 4 or 5 nanometer blue laser, basically from a Blu-ray player, and an algorithm to predict exactly how those waves would spread and interfere.
So they're calculating the fuzziness in advance.
Even better, they're pre-distorting the image. They use a DMD, a digital micromirror device. It's a chip with thousands of tiny mirrors that can flip on and off 17,000 times a second.
17,000 hertz.
Yeah.
That's just incomprehensible.
It has to be that fast to keep up with the spinning periscope, so the computer calculates this pattern that looks totally wrong to the naked eye. But as those light waves travel into the gel, they interfere with each other and converge to create a perfectly sharp point of light.
Not just at the focal plane, but anywhere inside that jar.
Anywhere. They've created a sharp focus across the entire 1 centimeter depth. They extended the depth of field by 20 times, all with math. No moving the lens.
Which explains the stats in the paper. A uniform resolution of 19 microns throughout the whole volume.
19 microns. A human hair is about 70 microns. So we're talking features that are significantly finer than a human hair, perfectly sharp, anywhere in that jar.
While the light source is spinning around it at 600 RPM. It just sounds too precise. I mean, how do they keep a spinning machine calibrated to the micron?
They thought of that. They built in an adaptive optics calibration system.
How does that work?
It's very clever. They put a fluorescent material in the jar, turn on the lasers, and then cameras watch where the beams actually hit versus where they should hit.
So it's a feedback loop.
Exactly. If the beam is off by just a tiny bit, the software sees it and tells the mirrors to shift the pixels to compensate. The whole system calibrates in just a few minutes.
And that's the difference between a cool lab experiment and a machine you can actually use in a factory.
Which brings us to the most exciting part. What can we actually make with this?
Well, the paper showed off some of the classics. They printed a Benchy.
Of course. The little tugboat. It's the hello world of 3D printing.
A torture test, really. Overhangs, tiny text. And they printed one in under a second.
They also printed a statue of Theodoric. It's a standard computer graphics model with a sword and shield, very complex geometry. They even CT scanned it, and it was a near-perfect match to the digital file.
But beyond tiny boats, the medical applications seem like the real breakthrough here, the whole sloshing problem. That's what prevented bioprinting before.
And Dish solves that. The door is wide open now. The source specifically mentions printing helical tubes,
which look a lot like blood vessels.
That's the idea, because they can use these watery, low-viscosity materials, things like Gelma or Silma. They can print soft, biocompatible hydrogels, basically structures made of water that cells can live in.
And since it's volumetric, you don't need support structures, right?
That is a massive advantage. Normally, to print a hollow tube, you have to print scaffolding inside it to hold up the roof, then you have to somehow dig it out later.
Which is impossible if the tube is microscopic.
Right. But with Dish, the gel itself is the support. So they can print these incredibly intricate vascular networks, even an elastic squid model that could bend and flex.
The paper even talks about in situ printing, printing an object inside something else.
Yeah, imagine a pipe in a factory with a crack on the inside. You could just fill the pipe with resin, shine the Dish periscope at it, and print a patch right there in place.
Or, and this is where it gets really sci-fi, in vivo bioprinting.
Printing inside the body. Theoretically, yes. The light only solidifies where the beams interfere, so you could inject a liquid and then solidify a stent or a scaffold directly inside a vein.
We're years away from that, obviously, but the physics works.
It does. But let's talk about something more immediate, the factory line. This was my favorite part.
Oh, me too. Because the jar doesn't spin, they realized they could just hook pipes up to it.
It's the industrialization of this concept. They connected the printer to a fluidic channel.
So picture it. Resin flows into the machine through a tube. The flow stops for 0.6 seconds. Zap. A solid gear appears. Then the pump flushes the gear out and new resin flows in.
Over and over, a continuous assembly line of distinct, customized 3D objects.
And because it's all digital, every single object in that stream could be different from the last one.
That's the key. You could print a gear, then a lens, then a hearing aid shell, all in the same stream of liquid without ever stopping the machine.
It kills the cost of change.
Right. No need to spend 50 grand on a new steel mold. You just upload a new file. It solves what some people call the trilemma of 3D printing.
The trilemma.
Yeah, usually you have to pick 2 out of 3. Speed, resolution, or material quality.
If you want it fast, it's low res. If you want it high res, it takes all day.
And Dash-H seems to offer all 3. Sub-second speed, 19-micron resolution, and the ability to use anything from hard plastics to soft biological gels.
Okay, so we're painting a very rosy picture. I have to ask the skeptic's question. What's the catch? Why aren't we printing cars with this tomorrow?
The catch is data.
Data.
Think about the math. To print 125 million 3D pixels voxels per second, with all those holographic distortion calculations for every fraction of a degree, the computational load is astronomical.
So to scale this up from 1 centimeter to, say, the size of a basketball.
You'd need a supercomputer just to process the hologram in real time. We're talking terabytes of data.
So for now, we're in the domain of the small.
Exactly. Microrobotics, medical implants, tiny custom connectors, that's where DIH will make its mark first. We won't be printing car bumpers with this method.
But for a custom hearing aid or a scaffold for a bone graft, it's perfect.
It is, and what's great is that it uses standard parts. That laser is from a Blu-ray player.
Huh?
That DMD chip is from an office projector. They just orchestrated the physics brilliantly.
It's just a reminder that sometimes the breakthrough isn't a new material. It's just looking at the problem, the spinning jar, and asking, do we really need to spin that?
A simple change in frame of reference.
So I want to leave you with a final thought on this. We live in a world defined by supply chains. We build things in factories, put them in boxes, ship them on boats, and they sit in warehouses.
The just-in-case model of inventory.
Right. But if a technology like DHH matures, where raw liquid goes in one end and a finished complex product comes out the other in less than a second,
the inventory disappears.
you stop storing things entirely. If the time cost of making an object is basically zero, the physical object is just the last step of a digital process.
You don't store the gear, you store the file in a tank of resin.
It pushes the just-in-time economy to its absolute theoretical limit. The product only exists the moment you actually need it.
That is a provocative thought. It turns manufacturing from a logistics challenge into a data management challenge.
Something to mull over. Thanks for listening to The Deep Dive.